organizers for inviting me to such a nice place with such wonderful people. Um, we have had quite a team of people working on MRFM at millikelvin temperatures. It began with Sasha and Andrea, who, together with Geert Weitz, uh, tried to do squid detection at low temperatures of the MRFM cantilever. They both come from the gravitational wave detector community, where they use squids to read out those transducers on big spheres that detect gravitational waves at millikelvin temperatures. And then we have had a team of many PhD students working more or less simultaneously on different projects. Um, and additionally, we really benefited from working together with Dirk Bouwmeester's group, with people in Delft that know a lot about superconductivity. And I'm very, very grateful to this list of people, many more, that introduced me to MRFM. But this was when I did a sabbatical almost 10 years ago now, with Dan and Martino and Christian and John. And recently we actually have a joint little project together with John Marone. I always need to list the technical people because also today I try to spend time on the parts of the work we actually spent a lot of time on, the technicalities. And we are very blessed that Heike Kamerlingh Onnes, he started a school of instrument makers in order to liquefy helium. And the school still exists. And on the board of the school are still many physics professors that make sure the school remains at the level. And here I listed the companies, and in red are the companies. If I mention them, you should be very, because I own shares in those companies. So there's a big conflict of interest. And did you notice, Rafi? He's looking for a place to do a sabbatical. So this is the image of Dan Rugar, um, where I've listed the ingredients that need to come together and have to come together in one place in order for the experiments to work. So usually the force sensor is optically detected, um, and then you need all these other ingredients as well. So when I learned about this technique, and I could learn it in Dan's lab, I said, okay, the field gradient is maximized. The friction of the cantilevers I thought was optimized, but of course it's been improved recently. And I thought, okay, I'll try to get the temperature as low as possible. So we replaced the laser interferometry by a squid detection. So there's a loop which can be the squid itself, or it can be a loop which is then transporting its flux to the squid. And I thought life would be so much easier if we would do this. So then of course comes the rationalization why we should keep doing this despite the troubles. So because of this detection, we're pretty much stuck with a magnet on the cantilever geometry. And then the way of making that sound good is then we can do any sample. We don't have to put the sample on the cantilever. And then the low temperatures, which are lower than most optically detected MFM experiments, could help us to do, say, oxide interfaces where superconductivity sets in only at 300 millikelvin, and then if you want to go below the transition. But if you look deep in my heart, this is the real reason why I keep on trying and make my graduate students' life miserable. So this is the electrical circuit. We have the magnet, which induces a flux in this pickup coil, which then goes sometimes through a transformer, but into the input coil to the squid. And then we have a little trick. We can inject a little flux And then we can calibrate this very, very accurately. And that will be important to the experiments later on. And well, here you see one of these companies, Leiden Spin Imaging. Um, um, this is the way we approach the sample. So we don't like to use the floppy autocube positioners, but I'm sorry. I talked to her already about some of these things. We also don't like very much to use these spindles from Janssen Precision Engineering because we don't know why, but they get stuck and we have to replace them. And it's actually quite some trouble to get this. But sorry, here I toggle between two images where you see this little ball. It's the magnet. This is the pickup coil and the RF wire. And if we move if we turn the spindles, we can approach the sample. And this is the good stuff where this sits underneath the dilution refrigerator mixing chamber. So it's actually quite large. And we're now testing the 8th version of a different motor, which is supposed to be much, it is much stiffer, but it's not using stick slip, because that should reduce the dissipation, and dissipation at 10 millikelvin, yeah, you have very little cooling power at 10 millikelvin. So we try to make a motor which does not slip, and that makes it very stiff. But as I said, it's the 8th version we are testing. But we're now, this is one of the reasons I like to work with the companies, even though they're small companies. It takes a lot of work and a lot of attention over a long time. And that is, for PhD students, very difficult, because they have other priorities in life than, they don't have 10 years time. While the fine mechanics engineer who works in the company, he has plenty of time. So we find the pickup coil, and then we can start doing our experiments. And we were very pleased that we could measure, say, down to 25 millikelvin, the thermal motion of this resonator. And the calibration is very accurate because we have this injection of flux, which gives a self-consistent energy determination. And this displacement sensitivity can be improved a little bit by optimizing the transformers and the sizes. The pickup loop, if it has the same size as the magnet, or then you get optimal coupling. But it also puts limits on how little vibrations you can afford to have on the chip which holds the force sensor. Because it's a high Q resonator, if this motion is a few picometers per root hertz, then the vibration of the chip better be Q times smaller than a few tens of piconewtons per root hertz. So picometers. And okay, always be careful if someone says easy MRFM, because these two words should never be very close to each other. But to get rid of the pickup coil on the chip, we now are working on getting the pickup coil right next to the cantilever, because then it will be easier to approach any sample, because right now any sample first needs to have a pickup loop and an RF line on it before we can study that sample. So this would be really a big step forward if we manage. So then, this is why a cryogen-free dilution refrigerator. There's actually not very many good reasons to do this experiment in a cryogen-free dilution refrigerator, because it says ch 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 and hits the sample. But there are some. So yeah, I have a little sound thing, but I already did it. So when we started these experiments in the early days, this would be a trace, and this would be all the, one of these peaks is the resonator. And so we zoom in between 1 and 6 kilohertz, and we zoom in more, and then there it was. So this was actually, because you hit the cryostat, and this is the resonance which has the highest Q, because it starts up here and then very slowly dies down, while the other die down quickly. So that's the way to find it, and it was not so pleasant. So we had to improve the vibration isolation. So our dilution refrigerator, this is the still plate, hangs from springs on this 4 Kelvin plate. And then we have an eddy current damper here. We also lifted the pulse tube, and then we have a heat link here, which should be soft. And then the vacuum, to make it vacuum, the vacuum seal should be soft as well. So I'll go very quickly through these slides because I don't have so much time. But it does help to do all these things. And here you see a first version of the copper braiding to make the heat link here. That helps to reduce the very low frequency parts. Here's a better version of the heat link. And the trouble is, and that's why we need fine mechanics engineers, is how do you weld this number of 50 micrometer sized copper wires? That is really a big challenge. And but then after all these things, we can calibrate by using the motion of the cantilever, which is our calibration. Then we can integrate all of this. And we find that it's actually low enough to, for example, do, I mean, STM, atomic resolution STM becomes easy if you have this very soft resonator at these kind of vibration levels. So I want to show you more pictures because all of these are gold plated. So we have three, this is the experiment of Dirk Bouwmeester. These are 2 experiments that we do. And here you see the high frequency vibration isolation system. So these are the springs here and there and there. And then we have these masses. Here is the welding of the heat link, which is on the inside now. And then it hangs from this. This is a normal spring, and this is a special mechanical fit. So this here you see the springs even better. So this is a very soft spring, and then this is a mechanical filter because there was a 10 or 20 kilohertz vibration coming from the switch of the pulse tube. So, I mean, these are very skilled people that did not get a PhD, but I mean, they might as well. So now things have cleaned up quite well. So this is the background noise of the squid. This is a little bit of 50 hertz that we did not clean up. This is the cantilever. And here's some microphonics left at very low frequencies. But again, it's below the angstrom level in the experiment. And so the final thing that I hope will clean up the low frequency part is that we put 2 frames. One stiff frame holding the cryostat. That will be on top of an island that weighs 30 tons. And then the other one holds just the pulse tube. And then if the pulse tube does not move so much anymore, then if the vacuum seal and the heat links inside are soft, then there will be very little force imparted on something that is very stiffly connected to something weighing 30 tons. So that is our hope to really make very low frequency mechanical experiments possible. So here you see this yoke holding the pulse tube. I mean, this stiffness must be 10 to the 8th newtons per meter. And here you see the softest vacuum seal that we have, but we have some ideas to improve that. Now, we have been working with 1 sphere. Nowadays we work with 2 spheres because this is then the sphere coupling to the pickup coil, and this is the sphere giving us the field gradient that we need. And we also try to do other things. So here we mill a film of platinum, iron platinum, which has a high remnant magnetization, and we managed to attach it to the force sensor. And this is the Maroon style. So you pick up one of these tiny magnets, where here the sphere is already on the other lever, except it ended up like this. So we'll meet again. Don't know where, don't know when. So here's another piece of equipment which does contain attocubes. Yeah, we do use attocubes. Inside the electron microscope, we can mount little things onto our levers, and it's a really nice toy. So why so much focus on technology? probably because the results are a little disappointing. So we do have really good force noise far away from the surface, and together with high field magnet gradients, it should work. But when we reach the surface, this force noise degrades because the Q goes down. So either one of these two things, would help these spins to behave better. But it's not so easy for us to use an external magnetic field because our squid is so sensitive. We can make a little coil, but then we also have to make a persistent mode switch to short circuit that coil once it's charged. And we actually did that, but the combination with the MRFM we did not do yet. And then there's another issue. How much heating do you generate at 10 millikelvin? You have such a small heat budget. If you send an RF current, do you heat the? So we've spent a lot of time on it. So here's an example of how the quality factor decreases for a sphere that is 3 or 4 micrometers large. If you are this far away from the surface, and as you go closer and you lower the temperature, your Q that was 50,000 is now only 2,000 or 1,000 even. And at the same time, the resonance frequency changes. And to understand that, you have to do the differential equations for the motion of the cantilever and the magnetic moment of all these spins. And then we can get these things to fit quite well, and we get reasonable numbers for the spin density and the T1 times of the spins that we wish were not on the surface, and then we could do really nice MRFM experiments. Then we say, okay, can't we turn this bug into a feature? Because we can measure spin densities also on other surfaces. And for example, we measured it on diamond, and then we find both the bulk spin density and the surface spin density. So this is the frequency shift we measure that we attribute to surface and bulk spins. And then in the damping, in order to get the fits nice, we have to include that the T1 time of spins increases if there's a strong field gradient, because then the spins that experience a large field gradient, they can't flip-flop relax to their fast relaxing neighbors. So I'm trying to sell this to my neighbors in Delft that do quantum computation and that would really benefit from knowing their spin density at different stages of fabrication. So Lieven van der Sijpen and Leo Kouwenhoven, they say, it's a good idea, we should talk about it. Which doesn't really help to get a large market for MRFM. I have a student who graduated, and one of his propositions was, within 5 years there will be a commercial MRFM. So we have 4 years to go. So here's our effort to reduce the dissipation in the RF wires. So we compare ourselves to the best RF wire to date for MRFM because of the virus imaging. And this is the large magnetic field gradient magnet. So we hope to stay below 100 millikelvin. And we find that the dissipation of a superconducting wire strongly depends on the frequency and the current, but we actually do reach values that we like. So we managed to stay below a microwatt at these frequencies, and this is for different currents. This is not necessarily the dissipation in the wire itself. It can be any contact resistance of the bonding wires, which makes this very hard to study. But okay, I can present some data of NMR on copper. We give a pulse during which we do not measure the resonance frequency, and then after the pulse we see the resonance frequency has shifted, and we see the decay, which is the T1 time of the copper nuclei. This is Boltzmann polarized, and we do this for different tip surface separations, and we see that the RF frequency fits the simulations that we have, since we know the magnetic moment of our particle and we know the magnetic field around it. we can calculate the spin polarizations, and we can see these signals. We can understand what they are. And there's one sharp peak here, and that is when we hit the next resonance. Let me skip this. So if we hit a higher mode of the mechanical resonator, we can actually generate a B1 field at very low dissipated power. So if need be, we can use this if we want to do NMR at very, very low temperatures, although it's limited to the mechanical frequencies that the resonator has. So let me use the last 5 minutes to say why I still pursue the very low frequencies and the very heavy mechanical resonators. So what I think about a lot with these people, so again, Dirk Bouwmeester and Roger, who wrote a nice paper about that, can we do a measurement that says something about the collapse of the wave function? So we would like to know, why does the arrow of a current measuring device not point two ways if we attach it to a squid that's in a superposition and where you know the currents are counter-rotating? Why does a measurement apparatus cause this to collapse? And we can think of ingredients that would make a measurement apparatus a measurement apparatus. Let me see. So what I always emphasize is that decoherence is not enough to explain the measurement problem or to understand what a measurement is. Because what decoherence does, it takes a density matrix, makes the off-diagonal element 0, and the diagonal elements are then the probabilities to end up somewhere. But after a measurement, also these diagonal elements are 0, and I just have one element that is 1. And that is, to me, is the measurement problem, not the decoherence. It's a problem to an experimentalist that tries to do a quantum experiment. Of course, it is. And so my take at this is that if I have a mass, then I have a corresponding gravitational field. And we are used to have this time evolution, but a gravitational field will cause time to run a little bit different. So time is a little bit slower than, because phi is negative, time runs effectively a little bit slower. But now if a mass is in two places at the same time, you don't know what your phi is. I mean, unless someone here knows what the gravitational potential is around a mass in superposition. So there are two ways out. One way is to say we don't know, and we have to measure whether it's this one or this potential, or maybe the average of the two. Or you have to say, no, these are separate universes. One universe has the mass here with this gravitational potential, and there is a separate universe that has the mass here and has this gravitational potential. Yes, that's my favorite way of justifying spending so much money and effort on this low temperature experiments. Of course, in order for this time evolution, this phase to be, say, let's say sometimes it's this potential, sometimes it's this potential, and we don't know which one, then after a long time of, you might get a phase difference between this potential and the other one of pi. So you need to wait for a long time until the product of the gravitational potential that you don't know times time times energy is something of the order of pi. And the way to calculate this time is to choose a large energy here, which is mc squared. And then you can predict that for micrometer-sized spheres, this should be after a second or a millisecond or a microsecond. I mean, somewhere in that ballpark could be reasonable. So let me emphasize that this is something I learned from Roger Penrose and Dick. So there are two ways forward for our group. If our force sensors are collapsing all the time already, then they might be heating up, because if you collapse something in a place and then time evolves again and then it collapses again, then you can imagine that it does not stay in the ground state. It gradually heats up. And that is in fact an experiment we did. This is to show how accurately we can determine the motion of